Alright, I wanted to do a couple exercises just because I haven't done this in a while, so just didn't want you to think that I had gone away for an extended period of time. Yeah, I've just been busy with doing research and stuff. I haven't had much time. Been focusing most of my math time on research rather than on making videos. Which, when you're getting into the deep of things with research, is not necessarily a bad thing. Um, but yeah, with teaching and everything, it's hard to find additional time to make videos as well. But anyways, so let's start on some of the stuff in chapter 3, which is where things start to get more interesting and more of what analysis really is about. Um, of course, chapters 1 and 2, all that information is necessary and it lays the groundworks for these types of proofs, but now we're getting into the more meat of things. Okay, so um, if a sequence Sn converges, we're going to prove that so does the absolute value of Sn. Um, so if the sequence, so basically what you do is you just apply the reverse triangle inequality to the sequence, and you're done. By the way, so you'll notice I typeset this. So I'm traveling for Thanksgiving, and I got back and realized that my stylus doesn't work anymore. So it probably needs a new battery, but tablet styluses need quadruple A batteries, and I left all of those at home. And it's not like I have quadruple A batteries lying around at my parents' house because no one uses them for anything except for pen styluses. Oh, I just realized we've got an issue here, but whatever. So anyways, no stylus, so I had to type it up. I tried doing that early Khan Academy thing where I just write it with my mouse, but that doesn't, it's not good. It does not look great at all. So anyways, if you have a sequence and it converges, okay, so to say that it converges means that there is some number, some real number s, such that given any epsilon you can find an n, such that beyond that n, your sequence is within epsilon of the limit s. So we want to satisfy this condition not for the sequence of Sn, but for the sequence of absolute value of Sn. So what we need is we need it to be true that this inequality, I don't know if my mouse shows up, so let me just write on it like this. We need to prove that this inequality is less than, we need to prove that this term is, we need to prove that given any epsilon, there is a capital N such that for any lowercase n greater than or equal to capital N, this term that I have underlined is less than epsilon. And so in order to find which epsilon, so given any epsilon, in order to find which n you use, you just use n from the previous part. You use the n that would work for your original sequence of SNs. And then you just can see by the reverse triangle inequality that norm Sn minus norm S, the norm of that thing is less than or equal to just the norm of Sn minus S. And in the original sequence, n was chosen so that this is less than epsilon. And so, yeah, that means that the absolute value of Sn will converge. So you just apply the reverse triangle inequality and it makes sense. And this sort of makes sense that it should converge because either if S is positive, then eventually everything's going to be positive, and so norm of Sn is exactly the same as norm of S. No, norm of Sn is exactly the same as Sn. If S is negative, then eventually all the Sn's are negative, and so you basically have the same n will work, and then, yeah, if it's getting closer to 0, or if S is 0, then maybe they're positive and negative, but eventually they get close enough. So yeah, this works. But anyway, so to say that the sequence of norm Sn converges means that the sequence Sn converges absolutely. And so that's a separate term in mathematics. I think the definition is given in this chapter. But the fact that it exists as a separate definition means that absolute convergence shouldn't be the same as convergence, because if it was, we wouldn't have two names for the different things. Um, if it was the same thing, we would have a theorem saying that like convergence is equivalent to absolute convergence. Um, and we wouldn't have a separate definition for absolute convergence. We would just say the thing that we normally call absolute convergence, we would prove that that's equivalent to convergence. But that's not the case. You have separate definitions, so you should expect that the converse is not true. And in fact, if you think about it, it's easy to come up with examples. And so you just let Sn bounce between +1 and -1. And then the Sns don't converge because you always are bouncing back and forth. But if you take that norm of Sn, you always get 1, and so it converges to 1. Of course, the norm and the bracket should be flipped here, but no big deal. But yeah, so that's how you go about doing this exercise. It's sort of like a warm-up to thinking about these things. And yeah, that's all there is to it.